Let's talk about network address translation in this video. This is also known as NAT. Before going into the details of network address translation, let's first understand why this was created in the first place. We all know that IPv4 is limited to 4.3 billion IP addresses at the max. But internet was growing at a rapid pace. A lot of new devices were getting added to the internet and it was growing on a day-by-day basis. This means people realized that the IPv4 addresses will be depleted very soon. So they needed a solution because they cannot restrict the internet size to 4.3 billion devices. So we needed a solution. So one of the permanent solution they have come up with is called IPv6. So rather than using just 32 bits for the IP addresses, we'll be switching to 128 bits. So IPv6 uses 128 bits for the addresses, which means the range is huge now. So theoretically, we'll never be in a situation where we'll be exhausting the IP addresses. But the challenge is we have built so many things on top of IPv4. We cannot just change everything to IPv6 overnight. We need a transition time. It's not going to happen immediately. So this is the permanent solution people came up with for the IP exhaustion issue. But even before IPv6 was introduced, people wanted a short-term solution because they were working out the details of the IPv6. So they wanted a short-term solution. So we will actually slow down the IPv4 depletion. So the short-term solution introduced for solving IP exhaustion issue is NAT. Okay, so this is what NAT. So now we'll understand how NAT works at a very high level. Okay, so in order to understand NAT, we first need to understand private networks. Okay, so let's imagine that we have two different networks. They are connected to the internet. Imagine that this is your home, and in your home you have a router. And you have connected many devices to that router so you can access internet from your home. So this could be your mobile phone, this could be your computer. So all of these devices which are connected to the internet in your home are connected through this router. So this could be your Wi-Fi router, or this could be an Ethernet based wired router. It could be anything. Okay, so we have a router that connects to the internet and your devices within the home are connected to this router. And on the other side of the world, for example, there could be, another router, another home, and where they could have two devices, and those two devices are connected to a router, and that router is connected to the internet. Okay. So before the introduction of NAT and the private networks, how this would have looked like is each of the devices that you have within your home need to have globally unique IP addresses. So out of the 4.3 billion IP addresses, we need to assign one unique IP address for each of these devices, including the router. And the same is true for the router on the other side of the world and also for these devices. Which means just for this setup, ignoring the internet here, for these 8 devices, we'll be using 8 different IP addresses, which will be globally unique. Okay, so this is the problem, right? With the introduction of private network, this network will be private, as in these devices within the network will not be exposed to the internet directly. Okay, so the router will play two roles. First of all, it will enable communication between these devices within the network, and also if any of these devices wants to connect to the internet, then the router will also facilitate that. But none of these devices within this network need to have public IP address. For the entire network, we can just have one public IP address, and each of these devices can have IP address from the private range of IPs, and they just need to be unique within this network. Okay, let's talk about what private IP is in a bit, but that's what it is actually. When we say the network is private network, the devices within the network uses the IP from private IP ranges, and we just need a minimum of one public IP address so all of these devices can access the internet. And that is what the private network is. Okay. Now let's quickly look at what private IP ranges are. So this was introduced when classful addressing scheme was still around. So we have 3 range of IP addresses. These are dedicated for private networks. So if any IP address is starting from 10 dot range, then this is one of the private IP address. In this private range, the first 8 bit is fixed. So if you pick a network ID, for example 10.5, then you are using first 16 bit for the network portion and the remaining 16 bit for the host portion. So that is one of the private network. And similarly, we have private ranges in class B and class C as well. So for class B, it starts from 172.16 and it goes up to 172.31. Okay, the last 2 octets can range from 0.0 to 255.255. Here the first 12 bits are fixed. Okay, so here again you can choose first 16 bit or first 24 bits as a network portion, and the remaining bits can be used for the host. And the last and the most used range is 192.168. So this is the range you'll use in your home network most of the time, because this is the smallest network possible in the private ranges. So for this, the first 16 bits are fixed and they always start with 192.168, and the remaining 2 octets can change. So let's say, for example, you could pick 192.168.10 as your network ID. In that case, you are using the first 24 bits for your network portion, and the remaining 8 bits can be used for host portion. If you do that, then you have maximum of 256 IPs, and out of which 2 will be used for broadcasting and network ID. So the remaining 254 IP addresses can be used for devices in your home. In most cases, you won't have more than 254 devices. So that is why this is popular choice for home private networks. Okay. So just to simply put, any network which uses these IP ranges are considered as private IPs. And the main reason why we consider these as private IPs is because any router or most of the routers won't route traffic which contains these IP addresses through public internet. So if you are actually sending a message to one of these IPs, then the router won't route this traffic through the public internet. Now, and also, if you are receiving message to one of these IPs, the destination IP address is one of these IPs, then that traffic won't get routed through the internet either. So router knows that these are private IP ranges, and it knows that it should not send these packets or route these packets through the public internet. So that is why we call these as private IPs. And this also adds a benefit that, if you want a network that is not exposed to the internet, you can use these private IPs for creating your network. Okay, so now if we go back to our diagram here, if you want to make this as a private network, all we need to do is we just need to use the IP address from the private range. Okay, so let's say, for example, we have chosen 10 dot range for the IP addresses, and our router might have something like 10.0.0.5 as IP address, and each of these devices may have different IP addresses within that range. For example, A might have IP addresses 10.0.0.1. Now, like I previously said, because this is actually private and we use private IPs, any of these devices are not accessible from internet, as in anyone cannot access these devices from the internet, and likewise these devices cannot access anything on the internet either. But that's not going to solve the problem, right? We wanted to access the internet as well. So what we will do is, the router will have a public address. It may have one or more public IP addresses. In this case, let's say the router has public IP address of 72.1.0.10. Now, if device A wants to access internet, it will send the message saying that it wants to access internet. Let's say, for example, it wants to access this device X on the other network across the world. Let's imagine that this is actually Google's network and this is actually google.com web server. Okay, so the user is trying to access google.com from this device. So it will send the message to router 1, and the destination IP address of this router 1 will be the IP address of this Google web server. Okay, again, on the other side, Google's network will also have private network. So these two devices will have private IP and the router will have public IP. So the message will be sent to the public IP address of this router 2. Okay, so we'll know the IP address of google.com, so that will be set as the destination IP address of the message we send. So the message goes to R1, and the router 1 sees that the message has come from this device, but it cannot send its IP address as a source IP address, because as we previously said, any message that contains source or destination IP address as a private IP address, then that message cannot be routed through the internet. So what it does is, it changes the IP address of that message, the source IP address of that message to the public IP address that it has. Okay, so this has the public IP address of 72.1.0.10. So when the message comes to router 1, it changes the source IP address from 10.0.0.1 to 72.1.0.10, and now that message is sent to the internet and it reaches the router 2. Okay, and then router 2 sends it to the Google's web server, and the response comes back to router 2, and that comes back to router 1 now. Now router 1 needs to know this response is for device A, because other devices are connected to this router as well. So this message could be any one of these devices. So it needs to know somehow that this message has come for the request made by device A. How it can know that this message is for device A? So this is where we have something called NAT table, and that table is going to help us to do this conversion. So if you are sending the message from device A to the internet, then router takes this IP address and it picks a unique port and it keeps a record of it. Okay, so when we get the response back, it looks at the table, the NAT table again, and identifies that this message is for device A, and it sends it to the device A's IP address and also to a write port. Okay, let's take a look at the example of this NAT table that will make things easier to understand. So this is an example of a NAT table, and in this table, if you see, we have device A's IP address, which is 10.0.0.1, and this is the private IP address, and this is the port that device A uses for this communication, and it uses port 5432 for this communication. And the public IP address that the router uses is 72.1.0.10, and it assigns port 8432 for this communication. So when device A sends the message to router, it will have this IP address and this port number, but the router changes this IP address and port number to this public IP address and this port number. So this will be the IP address and port number sent in the message that we send to the Google's web server. When Google's web server responds, it will set the destination IP address as this IP address and the destination port as this port. When the message comes to our router sees this. Okay, so this message has come for this particular IP address and this port number. Now it knows that, okay, so if it has come for this combination, then it must be for device A, and I need to send the message to this port. Okay, so it changes the IP address from public IP address to private IP address, and it changes the port number from this port number to this port number. Then it dispatches the message to device A. So this is how the whole round trip works. So if you imagine from Google's private network side, the same thing will be happening. When it receives a message, it knows that, this message is for this server because of the NAT table. And also when it replies, the reply also does the lookup on the NAT table, and it changes the source IP address and port number, and it sends the message to the internet. And we have different types of NATs. Actually, we're not going to look at them in detail, but just to be aware, we have different types of NATs. Static NAT, dynamic NAT, and NAT overloading are the most common ones. NAT overloading is also known as port multiplexing. So this is the example that we have seen here. We just have one IP address and we use different ports to avoid any collision. So each communication channel will have unique public port even if we have just one public IP address. Okay, so that is what the NAT overloading in its simplest form. Yeah, so this is at a very, very high level how NAT address translation works. So coming back to how this solves IP exhaustion issue, because we don't need to assign unique IP addresses for these private network devices across the world, we could use the same IP address on two different networks. For example, the Google's web server in this case could have the same IP address of 10.0.0.1 and will not have any collision because this network is a private network and the only interface, which is router, will have public IP address and which will be just one public IP address. And this is the practice we still use. If you take home network, this is what our setup looks like. Until we fully implement IPv6, NAT is here to stay. I hope this is useful. Thank you.